This is a real image of a robotic lander on the moon. You might notice that it's not exactly the right side up. This image is taken from a camera on the top of the vehicle, looking down. And as you can see, it's on its side with its landing legs sticking out. It was supposed to look like this when it landed. So how did we get here? NASA contracted a bunch of small companies to build lunar landers cheaply. This lander is called Odysseus and it was built by a company called Intuitive Machines at a total cost of $122 million. But still, it is a small company. They built a moon lander while only having 250 employees. So why use small companies? NASA has landed humans on the moon in the 60s, but at the time NASA had a peak budget of $67 billion yearly, adjusted for inflation of course. But since then, NASA's budget has gotten a lot lower these days, and their priorities were shifted to Mars for robotic exploration. If they wanted reliability, they could have used traditional aerospace contractors like JPL, Boeing, Lockheed Martin, etc. But that would have cost a lot more. Because consider that the Mars rover built by JPL costs $2.7 billion. Compared to that, Odysseus' costs seems reasonable. After being in development for almost 5 years, Odysseus launched on the Falcon 9 rocket on February 15, 2024. They were supposed to launch on the 13th, but a fuel loading issue on the lander caused the delay. Still, the launch went without issue, but after separating from the Falcon 9's second stage, the lander encountered a problem that almost caused the mission. The lander didn't know what orientation it was pointing in. Odysseus uses star trackers to know its exact orientation in space. Star trackers work by taking images of background stars, and since we know which direction and position in the sky all of the visible stars are in, just by taking a picture you can compare the picture with the existing database of stars that you already have and figure out which way you are pointing. But Odysseus' star tracker was sending garbage data to the flight computer. So the flight computer was like, what the hell are these numbers, star tracker, and didn't do anything. This caused Odysseus to tumble, doing one rotation every 40 minutes, and caused all sorts of problems. Firstly, the solar panels on Odysseus were pointing the wrong direction. So the batteries on Odysseus were not charging and they were running out fast. Communication was difficult because the antennas were pointing the wrong direction. This almost lost the mission. But even though the engineers at Mission Control didn't have any data on the orientation of the spacecraft, they still managed to figure out the rough direction Odysseus was pointing in. How, you might ask? The solar panels. If the lander is slowly spinning, then when its solar panel is aligned with the sun, it will receive power. But when it is pointing the opposite direction, it won't receive any power. So, when the batteries were running out and had only 3 hours worth of charge left, Mission Control did a bug fix that got Odysseus to point its solar panels in the rough direction of the sun for solar power, and they figured out that changing a parameter in the star tracker fixed its issues. Now the lander was in a stable orientation and was working well, but Mission Control still delayed starting the main engine and doing a firing test. The main rocket engine for this lander had never been fired in space before and used a somewhat novel fuel type, methane and oxygen. This was very different from the past engines used for lunar landers. Because in the past, spacecraft were using hypergolic fuel such as unsymmetrical dimethyl hydrazine and nitrogen tetroxide, which were toxic, corrosive, a health hazard and an environmental hazard. If you touch or inhale the stuff, you are going to have a very bad time. So, special protective suits need to be worn when working with spacecraft containing hypergolic fuels, and after fueling, the spacecraft had to be handled with care. So, a methane and oxygen engine in comparison is a huge improvement in terms of safety. And the methane and oxygen were a lot more efficient than hypergolic fuel as well, but they came with a different cost. Methane and oxygen need to be at very cold temperatures so they can stay as a liquid. Rocket engines aren't designed for gaseous fuel, because to store the same amount of methane and oxygen in gaseous form, you would need a way bigger tank, and that would be heavy. So for the fuel to stay liquid, methane has to be at negative 161.5 degrees Celsius and oxygen has to be at negative 183 degrees Celsius. And making pipes and valves that carry liquids that can handle very cold temperatures like that is hard. It is especially hard when you launch pipes and valves into space because you can't just fix it by sending a technician. And another wrinkle with methane and oxygen is boil off. Just like how water boils when you leave it in the sun for too long, cold liquids like this boil, even in space, because even though there are less molecules in space to conduct heat, the sun still heats spacecraft when it directly shines on them. So the methane and oxygen in Odysseus' tanks is being slowly boiled off by the sun, and the liquid is being converted into gas, and the gas is released from the tanks by valves that are on the spacecraft. Since there is no reason to keep gas around, that is useless because the rocket engine only works with liquids. So Odysseus is losing its landing fuel every second it spends in the sun. And the engine firing delay was caused because it took more time than expected to cool the pipes to the correct temperature and pass fuel through them. Because it is the first time the engine is in space, the engineers encountered behavior not seen when the engine is being fired on the ground. Also, the engine burn was delayed because of some communication dropouts. But they finally managed to do it successfully a day later than planned. Odysseus went on to fire it successfully for a couple of trajectory correction maneuvers, and this went without issue. And after reaching the moon, Odysseus fired its engines for 6 minutes and 48 seconds and successfully inserted itself into lunar orbit at a distance of 92 kilometers from the surface of the moon. Here is a picture of the lander in lunar orbit. It even managed to take a few clear pictures of the lunar surface with its landing cameras that it uses for terrain relative navigation, which is a fancy way of saying it's a camera used for choosing a good landing spot during the landing itself. It was supposed to spend 24 hours around the moon doing 12 orbits before starting its landing burn, but the landing time kept changing. They were initially targeting 10:49 p.m. GMT, and they did an orbit correction burn before that and actually moved the landing sooner and selected 9:24 p.m. GMT for the landing. Mission Control didn't have a lot of time to dilly-dally since the fuel on Odysseus was constantly boiling off. Each moment it spends not landing on the moon is a moment where fuel is being wasted to boil off. But as Odysseus was doing its pre-landing checks a couple of hours before it was due to land on the moon, Mission Control found that the laser altimeter was not working because it was actually completely turned off. An altimeter is something that measures how far you are from the surface. Planes have a dial that shows your height from the earth by using radar. The laser altimeter that is on Odysseus works similarly but uses lasers instead of radio waves since lasers require less power. But what do you mean the laser altimeter is turned off? I mean that they literally forgot to insert a small pin and wire harness that allowed the laser altimeter to work. The reason that it required a pin to work is because if the laser altimeter is turned on somehow when engineers are working on the lander, it might blind the engineers. So it was meant as a safety precaution to require a special pin to be installed just before launch. And they forgot to do it. This might seem like a silly mistake, but there were thousands and thousands of things they had to do before launch, and this was an oversight that they made since this was the first time that they launched a spacecraft as a company. This is an important point. Just because NASA landed humans on the moon before doesn't mean it's easy to do now. Because organizations don't have experience, people do. Most of the people that worked on Project Apollo are retired now or are no longer with us. So the workforce that has experience with lunar landers just doesn't exist right now. New experience has to be earned. And these people definitely learned from this experience because they did something that is just bonkers from a spaceflight software perspective. Though their laser altimeter didn't work, they had an ace up their sleeve. Because this lander wasn't empty, it was carrying many scientific payloads, like a camera designed to test how rocket engines affect the soil when it lands, a low-frequency radio receiver to detect the small amounts of plasma created when charged particles hit the lunar surface, and many more. But the most important for this situation is this: the Navigation Doppler LiDAR for precise velocity and range sensing, the NDL for short. Yes, they had another laser altimeter. The laser altimeter that didn't work was something that Intuitive Machines had developed, but this was an official NASA experiment, which, if it worked, would have been used on future NASA landers, maybe even human landers. But note that this NDL was only meant to be a test, not something that was actually used for landing. But it was still technically a laser altimeter. So Mission Control decided, let's just use it as that. This decision was crazy because, mind you, every piece of code on this lander has been tested and retested and has been in the works for years. So, changing spacecraft code last minute is just not done. Sure, there are many cases where software fixes have saved spacecraft from failure, but those were done slowly and methodically, maybe even taking days or weeks to be coded. But as I said before, they didn't have much time. Every second their precious fuel was boiling off and being vented from Odysseus. But since they had no options, they decided to delay the landing for only one more orbit. One orbit of the moon at the altitude they were in takes about 2 hours. And there is no info on this, but I don't think they had many hours left before the fuel became too low for landing. So the only way for Odysseus to survive was to develop a way for the data from the NDL to be transmitted to the flight computer and have the flight computer use that as the altimeter reading for the landing. And they did just that. This wasn't a bug fix like previously. This is an entire addition of a new feature. So the landing time had changed from 9:24 pm to 11:24 pm and it completed 13 orbits instead of 12 before landing. But they had done it. They completed the code and Odysseus started its landing maneuver. At 12 minutes 44 seconds before the landing, the main engine started up to slow the lander from going about 5,800 km per hour to 0 km per hour when it landed. The engine fired successfully and Odysseus maneuvered itself to the predetermined landing zone of the Malapert A crater, which is 300 kilometers from the south pole of the moon. Here is the mission control audio from the landing live stream as Odysseus went in to land.
We're tracking here in the broadcast booth. The clock has reached the expected.
May take a minute for comms to reestablish standby.
There it is, mission director beating us to it. We've reached the expected time of landing, but now is the process of waiting for comms, and we are in standby mode, as you heard it from the mission director, Dr. Tim Crane.
I was watching it live and for 9 long minutes there was no confirmation of a signal from the lander after the supposed landing time. But finally the mission director said this.
Signs of life, we have a return signal we're tracking.
So the lander wasn't dead yet, and after another 4 minutes we had this update.
And dial in the pointing for our dishes. What we can confirm, without a doubt, is our equipment is on the surface of the moon, and we are transmitting. So, congratulations IM team. We'll see how much more we can get from that.
The team celebrated because after a harrowing week of troubleshooting since the launch, they had done it. They had landed somehow. But exactly what had happened wasn't clear even to them. But they had done it, didn't they? They had made an extremely fast software patch that saved the mission. Or did they? It turns out that the software patch didn't work at all. On February 29th, during a press conference, they had explained what had happened. Take a listen.
We absolutely succeeded in remapping the geometry of the laser rangefinder laser beams to what the NDL laser beams were. And we did all of that in the navigation algorithm. The part we missed was there is a data valid flag that's set all the way back in the laser rangefinder itself. And we needed to populate that in the navigation software that we patched to basically hard code it to 1. And because we missed that, the navigation algorithm said, you've got measurements, but I don't see my data valid flag that I'm expecting from the original laser rangefinder. So those did not process after all. So basically we landed with our IMU and our optical navigation data flow algorithms, which were unique. It's the first time anybody's flown this algorithm, and it exceeded expectations because we lived to tell about it.
So NASA's NDL system hadn't worked at all, because a single bit of data which was supposed to be 1 to indicate that the data was valid was instead a 0. A simple programming mistake, but if you have ever done programming, it is obvious how someone would have missed this. because the code that connected NASA's NDL to the flight computer is completely correct, but the code that was already running on the flight computer was expecting a data value on the original non-functioning laser altimeter to be 1 to indicate that the data from the original laser is valid. So without an altimeter, the lander somehow managed to land by only relying on its terrain relative navigation system, which took pictures of the lunar surface and tried to find a landing site where the lunar surface wasn't too steep. And it also used its IMU or inertial measurement unit, which gave info about how fast it was accelerating. Odysseus was only designed to land on slopes that are around 10 degrees, but due to not knowing exactly how high the lander was, it skidded onto a lunar surface and the slope turned out to be about 12 degrees. Here is a real picture taken by the onboard camera during that phase of the flight. And it's pretty badass. The engine is still firing, so a lot of the dust is being kicked up, and the lander, skidding on the surface, broke one of its landing legs, as you can see here. Here is the Intuitive Mission CEO explaining the exact orientation of Odysseus.
We think we came down with, like I said, about 6 miles an hour this way and about 2 miles an hour this way, and caught a foot in the surface, and the lander has tipped like this. And we believe this is the orientation of the lander on the moon.
So that is how it came to rest on the surface like this. So this mission wasn't completely successful, and in hindsight there were lots of issues, but Intuitive Missions proved its worth as a company capable of persevering under difficult circumstances. Again, not many people have experience with designing moon landers, so it is better to give this team a chance to improve than give this contract to another company which needs to learn its lesson all over again. And Intuitive Missions will have a chance to prove it again. Intuitive Missions Mission 2 or IM2 is currently scheduled to be launched in a few months. And not only Intuitive Missions but other small companies like Firefly Aerospace and Astrobatic are gearing up for their next missions as well. And not to mention, other countries like India, China and Japan have had robotic landings as well, and crewed landing vehicles are being developed in America and China. So it seems 50 years after Project Apollo, the spotlight of humanity's space exploration is being shined on the moon once again.